Okay. Hi everyone. I am Alessandro di Giorgio, and today I will talk about Diagrammatic Polyhedral Algebra. I work in collaboration with Filippo Bonchi and Pawel Sobocinski. So, just to give you a little bit of history, Diagrammatic Polyhedral Algebra is the result of an extension of interacting of algebras, which in a few words is a sound and complete axiomatization for linear relations. And one application of it is the compositional modeling of signal flow graphs, which is a structure important in theory of control engineering and so on, to model basically linear systems. So our first extension of interacting of algebras is graphical affine algebra, where we move from linear relation to affine. Here the application is the modeling of electrical circuits. And finally, we come to diagrammatic polyhedral algebra, where we axiomatize, as we will see later, polyhedral relations. Here the applications are modeling of continuous Petri nets, where the tokens are not only natural numbers but also real numbers. As you can see here in the picture, the token gets splitted, for example. And also flow networks, which is what I will talk about at the end of the talk. So the very few categorical background we need is props, which are strict symmetric monoidal categories whose objects are natural numbers, and the monoidal product is addition on objects. So a first example of props is rel over a field K, in which every arrow from n to m represents a relation in k to the n times k to the m. The composition is relational, and the monoidal product is the Cartesian product. So in our approach, we establish a syntax and a semantics in terms of two categories, and specifically two props. And so the semantic interpretation is a functor between these two props, and so a propomorphism. So let's move to the syntax. The syntax is given by this context-free grammar, where we have 5 basic generators on the first row. Then on the second row, if you look carefully, we have the very same generators, but mirrored by the y-axis. And then we have 2 more generators, which are the cores for the extensions of interacting of algebras. And then we have the identity, symmetries, empty diagram, and of course the sequential and parallel compositions of diagrams. So as I told you before, we can, as anticipated you before, we can identify various kinds of relation in this language. And for example, if we consider only the fragments made of the first 2 rows, we can represent linear relations. Then if we also add 1 more generator, we move to affine, and then if we consider all of them, we move to polyhedral. So okay, as I told you before, we need a category to represent the syntax. This category is pdiag, and is the prop freely generated from the syntax. This basically means that the arrows of pdiag are diagrams, and here, for example, we have a diagram which has 2 wires on the left and 1 wire on the right, and this basically corresponds to an arrow from 2 to 1 in pdiag. Okay, the semantics instead is given in terms of rel over k, where k is now an ordered field, and this would be clear in a second why we chose an ordered field instead of just an arbitrary field. So we interpret our diagrams in terms of relations. So for example, let's look at this generator here, which is a copier, meaning that the semantics is a relation between x here on the left and a vector containing the same x twice on the right. Operationally, this means that whenever x gets in here, then on the two wires on the right, we have x again and again. Okay, the second generator is an adder, so it relates x and y on the left with x plus y on the right. So we get two inputs here on the left and get the addition on the right. Then we have a discharger, which has only one wire on the left and no wires on the right. So it relates x with the bullet, which is the single element of the only element of k to the 0. Then we have the 0, which outputs 0 here on the right and has no wire on the left. And then the last one is an amplifier. Actually, we have one of them for each element of the other field. What it does is take x here on the left and outputs x times k on the right, so it amplifies x. Okay, if you recall, on the second row of the syntax, we have all these generators but reflected. For example, one of them is this one, which is the addition reflected. And this is also in the semantics, because its semantics is the relation between x plus y on the left and xy on the right. So it's basically the opposite relation of this relation here, which turns out to be the semantics of the original version of the adder. And this holds for all the mirrored diagrams, that their semantics is the opposite of their original version, let's say. Then we have the extensions. Here we have the 1, which acts like the 0, but it outputs 1 on the right instead of 0. And then we have the greater than or equal relation, which is mapped to the obvious greater than or equal relation. And then we have the identities, the symmetries, and the empty diagram, whose semantics is pretty straightforward. Okay, finally, we have the semantics of the sequential and parallel composition, which is functorial. So it basically means that we first compute the semantics of the single parts, and then we put them together via the relational composition, so the sequential composition in REL, the semantic domain, and Cartesian product, so the monoidal product in REL, again, the semantic domain. Okay, to give you a first example of what we can do with this diagrammatic language, let's look at this matrix here on the left and at the diagram here on the right. So what I will show is that this diagram, in some sense, models the behavior of the matrix. If you consider, for example, multiplying this matrix by the vector for 1 and sending as an input 4 and 1 here on the wires of the diagram, then if you use the rules of the semantics I just showed you, we see that this 4 and 1 gets copied by the copiers. Then this 1 here gets multiplied by this black box, which is syntactic sugar for a -1 amplifier. And so 1 gets multiplied by -1 and we get -1. Then the other two amplifiers do their work. And so 4 becomes 8 and -1 becomes -3. And then 4 and 1 here slide through the identities and we get our first two outputs. And then 8 and -3 gets added by the adder and we get 5. So if you do the math, you will see that this 4, 5, and 1 is exactly the result of the matrix multiplication. Now we have a result from interacting with algebras, which basically states that for any m times n matrix in A, m times matrix A, sorry, with entries in K, we can associate a diagram of this form, which we will abbreviate in a box with an A in it, and having a label n and m on the wires, representing the fact that A has n wires on the left and m wires on the right, which are basically the columns and the rows, respectively, of the matrix. Now, the semantics of this diagram would be, of course, the set of all pairs x, A times x. Okay, polyhedral relations. So I recall you that a polyhedron is one of its many description is the set of solution of these systems of inequalities. We can look at it as a relation, meaning that we can look at this vector z in n plus m as a pair x, as a pair of vectors x and y in k to the n times k to the m. But basically, it's the same polyhedron. So to represent it diagrammatically, we have all the ingredients we need. Indeed, we can represent the matrix A and the vector B as a one-column matrix. And then we can observe that B here is multiplied by 1, and then we can close its single wire on the left with a 1. Then we can move it from the right of the greater than or equal relation to the left and then change its sign, and so multiply it for the black box as we saw earlier. And then we add them together with the other, of course. And what is left is the greater than or equal than 0 constraint, which is pretty straightforward, is modeled in this way. Okay, now we have a diagram with n plus m y's on the left and 0 y on the right, but we would like to look at it as a relation. So we would like to have these m y's here representing the y on the right. And so what we can do is to bend the wire using the copier and the mirrored discharge. If you compute the semantics, this will be exactly a bent wire. Okay, now the main result of this work is its axiomatization, meaning a set of equalities and inequalities between diagrams. Some of them express very well-known algebraic structures. So, for example, here we are stating that the copier and the other are commutative, are associative, and have a unit. Some of them reflect the fact that K is an ordered field. So, for example, here we have anti-symmetry. Some of them express the interaction of the greater than or equal generator with the other generators. And some of them also involve the one generator. Now, I will not talk about the axioms. There are more of them, but the key point is that they are sound and complete with respect to the semantics. So basically it means that whenever we can equate two diagrams in terms of these axioms, then also their semantics in terms of polyhedron is equal and vice versa. So this basically gives us a way to reason about polyhedra in a completely axiomatic and diagrammatic way. Okay, as anticipated you at the start of this talk, we can model systems with some notion of bounded resources. And one example is flow networks, which I recall you is basically a directed graph in which we have a source node and a target node, and all the edges have a label which expresses a capacity, meaning that, for example, in this edge, I cannot get a flow which is greater or equal than 6. And a natural question to ask on flow networks is, what is the maximum flow going from S to T in this network? And okay, there is a very well-known result which tells us that the mean cut of the network is equal to the maximum flow, and in this particular case, it is 5. Okay, we will keep this in mind for later. Okay, to translate from the usual notation for flow networks to our diagrammatic language, we encode any node with n incoming edges and m outgoing edges as the composition of an n-ary adder with an m-ary mirrored adder. And this is basically stating that the sum of whatever is incoming is equal to the sum of whatever is outcoming. And this is an unusual property to ask on flow networks. Regarding the edges, instead, we map it to this diagram here, whose semantics is basically the set of all x and x, so like an identity, such that x is between 0 and k. So basically exactly the meaning of an edge. Now for brevity, we will use syntactic sugar for this diagram and represent it as a box, a yellow box with a K in it. But again, it's just a syntactic sugar. So now let's look at some operation I can do flow networks on parts of it. One of them is edge contraction, which basically says that whenever I have a network or a piece of a network in this shape with an edge labeled with K and an edge labeled with Q, all having the same source and target, then I can contract them and represent it as a single edge with K plus Q capacity. This is represented as the following derived law, in which which basically says exactly what I say now. Okay, one other operation is the redundant constraint elimination, which says that when we have a diagram network, in the shape, having two incoming edges labeled with K and Q, and one outgoing edge is labeled with L, such that K plus Q is less or equal than L, then we can drop this L because it's non-linear constraint, since K plus Q will never exceed L. So the flow will never exceed L, and then we can basically replace it with infinity. This is easily represented by this law, where basically we drop this constraint here. Now notice that these laws are perfectly provable with the axiomatization, which is, as I told you before, complete. Okay, now let's go back to the example I showed you before. This network here is represented by this diagram here of Diagrammatic Polyhedral Algebra, and let's see how we can apply the laws I just showed you. So, for example, in this part of the network, we can apply the redundant constraint elimination, since 2 plus 1 is less or equal than 6, and so drop this constraint here. We can do the same on this other part of the network and drop the 5. Then we can apply the commutativity of the addition and then reorder the wires in order to apply the edge contraction on this part here and get 3 out of 2 plus 1. Again, we can apply the edge contraction and get 5, a single edge with 5. Now, if you recall, the minimum cut, which is also the maximum flow of the network, is 5 in this example, and we moved from representation of the whole network to the representation of a single edge between two nodes labeled with 5. So basically what we did is to compute the maximum flow of the minimum cut in an axiomatic and diagrammatic way, exploiting parts of the networks which can be rewritten according to the laws and the axioms of the theory. So what I showed you to conclude is a complete axiomatization for polyhedra, which is a topic not usually explained in terms of an axiomatic theory. And this makes us believe that our approach, our algebraic approach, is suitable for automating proofs in theorems provers about theorems involving polyhedra, and there are many of them in the literature. You can think about, for example, Farkas lemma or linear programming dualities. but also you could use it, for example, to prove correctness about algorithms involving flow networks or systems in which you have a notion of bounded resources. Okay, as a future work, we leave the discovery of other laws for flow networks, and so to find some sort of algebraic theory precisely for flow networks. And also a stateful extension, which is discussed in the appendix of the paper, which is the addition of a single generator expressing the state to our language, and let's see how it reflects on the theory. There is already some work which has been done, which, as I anticipated you at the start of the talk, let us model continuous Petri nets. But again, there is more to do there.